Dear students, welcome to the theory session number 12 in the chapter of chemical bonding in physical chemistry. In our last theory session, we were discussing about the molecular orbital configurations for the heteronuclear diatomic molecules. In our theory session today, we shall be discussing about those heteronuclear diatomic molecules, and then we will try our hand at the molecular orbital diagram of different homonuclear diatomic molecules, for example hydrogen, nitrogen, oxygen, etc. So moving onwards with our discussion, we will now do the MO configuration for NO plus 2 cation. So we had already discussed about the configuration for NO or nitric oxide. Now we will be discussing about the NO plus 2 cation. So nitrogen, which has a configuration 1s2, 2s2, 2p3, there are a total of 7 electrons. And in oxygen, which has a configuration 1s2, 2s2, 2p4, has a total of 8 electrons. In both the cases, I am just keeping myself concentrated on the total number of electrons and not only on the valence electrons. So on a total, we can say there are 15 electrons minus 2 electrons because of its plus charge. Therefore, we have to settle a total of 13 electrons in NO plus 2 cation. Now, if I write the MO configuration, it will be like this: sigma 1s, then sigma 1s star, then we have a sigma 2s, then sigma 2s star, then we have a pi y is equal to pi z, then we have sigma x, then we have pi star y is equal to pi star z, and lastly we have sigma star x. So this is the order of the relative energies in case of a heteronuclear diatomic molecule. Now the arrangement of the 13 electrons will take place according to the Hund's rule for maximum multiplicity, the Pauli's exclusion principle, and obviously the Aufbau rule. So the arrangement will take place like this: 1, 2, 3, 4, 5, 6, 7 and 8, 9, 10, 11, 12, and there is 13. So therefore, we can write this MO configuration as such: sigma 1s 2, sigma 1s star is also 2, sigma 2s 2, sigma star 2s also contains 2 electrons. Then you have pi y containing 2 electrons equal to pi z, which also contains 2 electrons. Then you have a sigma x containing 1 electron. So we can see that NO2 plus molecular ion is paramagnetic in nature. Why is this paramagnetic in nature? This is due to the presence of the unpaired electron in the sigma x orbital. So you have this unpaired electron in the sigma x orbital, and hence it is paramagnetic. So if I calculate the bond order is equal to Nb minus Na divided by 2. If you remember that Nb is the number of electrons in the bonding orbital, Na is the number of electrons in the anti-bonding orbital, and we will divide the whole number by the 2. Therefore, calculate the number of electrons in bonding orbital. This is 2, 2, 4, 5, 6, 7, 8 and 9. And in the anti-bonding orbital there are 2, 2, 4. So the bond order is equal to 9 minus 4 divided by 2, that is equal to 5 divided by 2, which is equal to 2.5. Therefore we can say that NO plus 2 has a bond order of 2.5. So this was the discussion about the NO plus 2 cation. Now next we will discuss about the NO minus anion. So moving on with our discussion about the MO configuration. Nitrogen having a configuration 1s2, 2s2, 2p3 has 7 electrons in the outermost shell. Oxygen, which has a configuration 1s2, 2s2, 2p4, has a total of 8 electrons. So there are total 15 electrons plus 1 electron because of the negative charge. Therefore NO minus anion contains a total of 16 electrons. So the MO configuration can be written as sigma 1s, sigma star 1s, sigma 2s, then you have the sigma star 2s, then you have pi y is equal to pi z, then you have sigma x, then you have pi star y is equal to pi star z, and lastly you have sigma star x. So if I arrange the 16 electrons in the 16 electrons in the NO minus anion, then the arrangement will be as follows: 1 and 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. So this can be written accordingly: 1s2 sigma star 1s2, sigma 2s2, sigma star 2s also 2, then we have pi y2 is equal to pi z2, then you have sigma x2, then you have pi star y1 equal to pi star z also 1. So this arrangement in the MO for the NO minus anion is according to the Aufbau principle, the Hund's rule for maximum multiplicity, and also the Pauli's exclusion principle. So if I calculate the bond order of NO minus anion, it will be like this: bond order is equal to NB minus NA divided by 2, where NB is the number of electrons in the bonding orbital minus number of electrons in the anti-bonding orbital divided by 2. So the number of electrons in the bonding orbital is 2, 2, 4, 5, 6, 7, 8, 9, 10. So there are 10 electrons in the bonding orbital. And the number of electrons in the anti-bonding orbital is equal to 2, 2, 4, 5 and 6. So you have 10 electrons in the bonding orbital and 6 electrons in the anti-bonding orbital. So it is equal to 10 minus 6 divided by 2, which is equal to a bond order equal to 2. Therefore we can say that NO minus anion is a double bonded molecule which has a bond order equal to 2. So these are the discussions about the NO minus anion. And also if we discuss about the magnetic character of NO minus, we can say that NO minus anion is paramagnetic due to the presence of unpaired electrons in its molecular orbitals. So there is a presence of unpaired electrons in the molecular orbital, and hence it has the paramagnetic character. So these were the discussions about NO plus 2 and NO minus anion. Now one good discussion will be about the molecular orbital configuration of the hydrogen fluoride molecule. So if I talk about hydrogen fluoride is also a heteronuclear diatomic molecule. So let us discuss about the MO configuration of HF molecule. So this is composed of one hydrogen and one fluorine atom. So this gives rise to the hydrogen fluoride. The configuration for hydrogen is 1s1, and the configuration for fluorine is 1s2, 2s2, then there is 2px1. Sorry, if I write this, it will be 2px2, 2py2, and 2pz1. So this is the configuration for fluorine. So fluorine atoms which has a total of 9 electrons. So in the formation of HF molecule, there will be the overlap will be in between the 2pz orbital of the fluorine atom and the singly filled 1s orbital of the hydrogen atom, and there will be formation of 2 sigma molecular orbitals known as the sigma bonding sp and the sigma sp star. So there are 2 particular molecular orbital formations. 2 electrons, one from this 1s orbital of the hydrogen and one from this 2pz orbital of the fluorine, now will occupy this sigma bonding sp molecular orbital. Since the energy of this sigma bonding sp is less than that of sigma star sp orbital, and the remaining 6 electrons of the fluorine atom remain in their respective atomic orbitals. So the molecular energy level diagram shows that the molecular orbital configuration of hydrogen fluoride molecule can be written like this. So if I write the MO configuration, it is this will be 2s2 sigma bonding sp 2, 2px2, 2py2, and sigma sp star 0. I am only concentrating in the valence level and not the inner lining electrons. So here the bond order comes equal to bonding minus anti-bonding electrons divided by 2, which is equal to 1. So the bond order of the hydrogen fluoride molecule is equal to 1. So in our molecular orbital discussion, we did our discussion on the homonuclear diatomic molecules. Also we have discussed in detail about the heteronuclear diatomic molecules of different kinds. Now the most important part of the MO theory is the drawing of the molecular orbital diagrams. So now we will focus our discussion about the diagrams of the molecular orbital theory.